images is here. Okay. Just a few minutes, guys. Okay, so we are now on chemical reaction engineering. So the second of the fourth courses in which I'm going to cover for you. And we will divide our review into two parts. That would be the reaction kinetics, or simply the kinetics, and then the reactor design. So for this afternoon, we'll be discussing, we're having a review for 2 hours, and we'll just concentrate first on kinetics. Then next meeting, we will have reactor design already, so that we will you'll be able to focus. Now for kinetics, so we have this one. You know, for one, that when we speak of kinetics, it is the study of how fast a reaction occurs. Now, there are 4 important factors that we need to consider in terms of the rate of reaction. So, temperature, concentration, surface area, and the action of catalysts are all factors that are to be considered in terms of accounting for how fast the reaction proceeds. So, take note of that. Temperature, the presence of the catalyst, the concentration, and the surface area if you have solids present in your system. Now, for constant volume reactions, the speed of reaction is actually measured as an average. So when we speak of the average rate, we just take the difference of two concentrations and we divide it over the time in which this particular concentration values were taken. So for instance, you're given this particular reaction of A being converted to B. When we speak of the average rate, we just simply take into account the change in the concentration of B over the change in time. So it's really very different when we say the average rate or the instantaneous rate. So what you have learned in your chemistry then is just the average rate of reactions. If you are taking the differences of the two values, concentration and time. So this is average rate. Now, for this one, the speed at which the product appears, that is the change in the moles of B per unit time, can be the basis of the reaction rate. Or it could be also the speed at which the reactant disappears, and that is the change in the moles of A per unit time. It's the same thing when we talk about instantaneous rate. So when we speak of the speed of a reaction, whether average or instantaneous, it could be based on a particular species that is present in your reaction. It could be the product, so the speed in which that particular product is being formed, or it could be any of your reactants, and it would be the basis this time of how that particular reactant is being consumed in the course of the reaction. So either of the two, but still you are expressing the rate of that particular reaction. Only that it depends on the particular species in which you're going to base that particular rate. So average rate with respect to A is the change in the concentration of A divided by the change in time, or the difference in time. Now you see here a negative. Why do you think is this? Do you have a negative sign in here? Anybody who knows the reason behind why you have negative of the change in the concentration of A divided by the change in time, or the difference in time? When you speak of average, okay, somebody wrote in the chat box, consumed amount. Kaka-consume an A over time is. So if A is being consumed, thank you for your answers. If A is being consumed in the course of the reaction, it follows that this change in the concentration will be negative. And since you're being asked about the average rate, you cannot answer a negative value. So to compensate for that negative drop or a decrease in the concentration of A, just like what your classmate have mentioned in the chat box, then we have to write a negative sign in here. That way your answer will be positive at all times. It's because of the term average. You don't answer a negative value for an average or for if you're asked about the average. So your answer should be positive. So that's the purpose why you have here negative. Okay? Because in here, your concentration for A drops over time. So the difference will be negative. Okay? So we move on. Now, what about the change of rate with time? So for the reaction of A, there are two ways of expressing the rate: the average rate and the instantaneous rate. So the average rate I have mentioned already. So most useful units of rates look at molarity, so mole per liter. Since volume is a constant, molarity and moles are, of course, directly proportional. So when you speak of rate, it has to be molarity over time, or mole per liter per unit time. Most of the time it's per second, but when we're dealing with English set of units, the common set is pounds per cubic feet per hour, or pound moles rather, pound moles per cubic feet per hour. That is if the set of units is English. If it's SI, oftentimes it's mole per liter per second, or mole per cubic meter per second. Now, let's say, for example, you have this particular reaction in the formation of an alcohol, butanol, and let me just proceed. And you have this table that accounts for the changes in the concentration of the reactant. You have here the changes in the concentration of the reactant over time. So you could see that when we account for the average rate, we take the difference of two adjacent concentration differences. So we don't, it's not suggested that when you take the average rate, you get one concentration here and you get one concentration here. Of course, the difference in time will be starting from 0 to this 800 seconds in here. Oftentimes, if it's average rate, you take the next value or the two adjacent values in your empirical data, in your set of empirical data. So what we have here in the third column are the average rates based on these changes in the concentration of our reactant. Now, if this concentration, on the other hand, is plotted against time, this would be how it would look like. So this is how your paired values of concentration of the reactant with respect to time behave. So over time, the concentration of your reactant decreases. Now, when you speak of instantaneous rates, it's really different with that of the average rate in the sense that you could see you are to draw a tangential line on that portion of the graph wherein you're interested of measuring that the rate of the reaction at that particular instance. So for example, allow me to project just for this time so it would be bigger. So for example, we want to know the instantaneous rate of your reaction after 600 seconds in which it has started. Okay, so 600 seconds from here on the horizontal axis, you go up, you project it on the curve which you have made, drawn smoothly on the paired values of concentration and time, and you draw a tangential line on that particular portion of the curve which you want to determine the instantaneous rate. So the slope of this particular tangential line on that particular time you want to measure the instantaneous rate is the instantaneous rate. So you have to get the slope of this tangent line at this time, which is 600 seconds. That would then be the instantaneous rate of your reaction at 600 seconds. So it's different. So I would like now to go back. So it's different when you are to get the average rate because you are really required, although in here you are required to have this plot, in taking the average you are required two pairs of data. A pair of concentration and a pair of time elapsed for such concentrations when those particular concentrations were measured. So this is actually very elementary but very fundamental in nature, and as such, I am explaining it to you. The difference between average and instantaneous rate. Now, in kinetics, what we are measuring actually is the instantaneous rate. At that particular instant, what is the rate of the reaction? Because when you speak of average rate class, it's like they say, on the average, after an hour, what is the rate of your reaction? So you take the difference between the starting point concentration, the starting time concentration, and the concentration after an hour. So you don't know exactly at any particular time in that after 1 hour, what is the instantaneous rate. So those are two very different things. Okay, now we proceed. Now, so for our reaction, the rate can be expressed in terms of average. In this case, you are taking the change in the concentration of the species, and then over time, in here, you're taking the change in the concentration of the product over time. So the change in the concentration of the product is positive. It's written as positive because we expect that this one will increase over time. So it's positive. As for our reactant, it's negative because it's expected that the rate is, of course, the change in the concentration will be negative over time. Now, another very fundamental concept in kinetics. So I'd like to project this. Just let me know if, sorry, if this is not, if it cannot be seen by you. Okay. And I have emphasized this when we were covering this topic last year. Excuse me. So when you write the rates of reaction and even the relationship of the, shall I say, the amounts of the species at any particular time in reference to the stoichiometric equation. So when we speak of the stoichiometric equation, this is the stoichiometric equation. Now, in kinetics, we discussed that the amount of A that has reacted divided by the coefficient of A in your stoichiometric equation is equal to the amount of B that has reacted divided by its coefficient as well, based on the stoichiometric equation, equal to the amount of C that was formed, because C now is a product, divided by C, and same thing with the D. This is fundamental, and you should remember this. This is just like the ABCs of kinetics, because whether your reaction is elementary or non-elementary, this particular relationship holds. Now, it's the same thing in here with the average rates of reaction expressed on each of the species that you see, A, B, C, D, divided by the coefficients of these species as they are written in the balanced chemical reaction. It's the same thing. Another thing that you can add to this is in terms of rates, actual rates. Like you say the rate in terms of A divided by A. When you speak of the rate in here, this is an actual quantity, not an expression. Okay. Rate in terms of B, rate in terms of C, and rate in terms of D. Now, I have written the C and the D as positive because they are products of our reaction. So this is really, really very important and it's fundamental. It's a fundamental concept in kinetics. So please don't forget that one. Just clear my markings. So that's it. So it's just, I'm just reiterating it here based on the, I can't skip this one. Okay, based on the average rates and the relationship of the average rates based on the stoichiometric equation. Okay. Now, in general, rates increase as concentrations increases. So the rate of reaction increases as we increase the concentration. So as you could see in here, this I would like to have this again, a projection. I hope you can see. So in here, you could see that you have here the initial concentration of ammonium. Let's say that's A. The nitrite and ion, you have nitrogen, and you have here water. So the initial concentration of the ammonium here, of ammonium, and you have the initial concentration here of nitrite, and the observed initial rates of reaction. So you could see that as we increase the initial concentration of ammonium, so you can see here an increase, there's a corresponding observed increase in the rate of reaction, keeping the concentration of B constant. Again, so if I would increase the concentration of A, keeping the concentration of B constant, there's an observed rate increase, or there's an observed increase in the rate of reaction, as you can see here. Doing it another way around, if I keep the concentration of A constant, then this time I will increase the concentration of B, there's also a marked increase in the rate of reaction. How do we interpret now this particular set of empirical data of the reaction written on top? Okay, so let's proceed on the next slide.
Hello, Miss.
You don't see?
Miss, wala. Miss, naka-share screen, Miss. Ang, ano. Okay na, Miss.
I think the problem is with my laptop. Okay. Now, in here, where was I? So this is the one that I'm showing a while ago, the table. And these are the things that we have observed from the table. So as A, the ammonium doubles, your nitrate concentration constant, the rate doubles. So let's see. So you can see that there's more or less a doubling in the rate here. If we double the concentration, the rate also doubles, more or less. Okay, this one in here, we don't see the doubling. But in this case and in this case, we are doubling the concentration of A, and more or less there's a double also. The rate of reaction also doubles. So that's what it meant here. So as A doubles with B kept constant, the rate doubles. As species B is doubled, so that's your nitrate is doubled, your ammonium kept constant, the rate doubles as well. So if we go back, you can see here that if this time we double it in here from this value to this, actually this one is not double. We have here a doubling for 0.0404 and 0.0808. And more or less, if you multiply this by 2, you will have this one. That's it. In here, we've kept constant A, or our ammonium. So there's a doubling in the rates if the concentration of the species A and B double. So then we say that the rate is directly proportional to the concentration of these two reacting species. Now we write then the rate law as this one. It's directly proportional to the product of the ammonium and the nitrate and ion. So you could see it in here. The constant K is the rate constant. So generally, this is how we do it. We are asked to interpret the given set of data and come up with the rate law that will represent the given set of data. But in kinetics, as what you have learned last year, we have several techniques to use in determining the specific value of N and K, not just simply doing inspection. Like what happens to the rate if I double the concentration of one and keeping the concentration of the other constant. Because oftentimes when you're given an empirical set of data, it does not come in this form. You're not given two, or rather three sets of information wherein one set, the concentration of one species is constant, the other, it's varying. And then in a different scenario, the other one that was varied first was now kept constant, and the first that was constant was varied. No, we don't have that in kinetics, but rather when you interpret kinetic data, you're only given one particular set of concentration value against time, or one particular set of concentration value against rate. So it depends on what the problem gives, but it's only coming in pairs. Now in this one, you have three sets of values already. So if that is the case, then that's how you should look at it and how you should come up with the rate law by inspection, taking into account the behavior of the concentration of one with respect to the rate of reaction, one species with respect to the rate of reaction. But if you're given a pair of information, it could either be concentration and time, conversion and time, or concentration and rate, then you really have to recall what was used in, or what the techniques that were used in your kinetics last semester. Okay, and we will review those as well. Now, for a general reaction with rate law written in this form, so let's say, for example, your rate law is written as K times the concentration of reactant 1 raised to M and reactant 2 raised to N. We say that the reaction is mth order with respect to reactant 1 and nth order with respect to reactant 2. Okay? Overall, the order of the reaction is the sum of the exponents to which these concentration terms in your rate law are raised to. So you take the sum of these two exponents, that would be your overall order of the reaction. Now, a reaction can be zeroth order if you don't have any concentration term appearing on the right side of your rate law. Okay? No concentration term, meaning if you raise this to 0 and you raise this to 0, both are actually equal to 1. So you don't see them anymore written. So you only get to see a K. That is the case, your rate of reaction is not dependent on changes in the concentration of your reacting species. They may depend on some other factors as discussed. So it could be either in terms of the surface area of the solid catalyst, if there are solids present in your system. It could also be based on the degree of radiation in your system, especially for photochemical reactions. So it could be dependent on some other factors except concentrations or concentration of your reacting species. So note the values of the exponents or the orders have to be determined experimentally. So you are to be provided with a set of empirical data that way you can come up with the correct N and K for your rate law for a particular reaction. So they are not simply related to stoichiometry. They could be related to stoichiometry when it's really specified in the problem that your reaction is elementary. And that's a part of the journey already of solving a kinetic related problem, because you know already that you have an elementary reaction. The problem is quite a challenge if it's not stated, or the elementary is non-elementary, and the reaction rather is non-elementary. So in that case, class, it's a no-no to assume that your reaction is elementary if it's not stated in the problem. So it has to be stated in the problem. Now, using initial rates to determine rate loss. So how do we determine rate loss using initial rates? So a reaction is zero order in a reactant if the change in the concentration of that reactant produces no effect. Okay, so if you're given a set of empirical data that you are to interpret, and over the changes in the concentration of that particular reactant, you don't see or you don't observe any changes in the reaction rate. So meaning the concentration of that particular reactant is not a factor in considering the rate of reaction. So in terms of that particular reactant, your reaction order is said to be 0. Now, a reaction is first order if doubling the concentration causes the rate to double. So we can say that it's directly proportional. You double the concentration, the rate doubles. You triple the concentration, the rate triples. So they are directly proportional. So it's first order. The order of the reaction is first order with respect to that species which you use as a basis. Now, a reaction in general is nth order if doubling the concentration causes a 2 raised to n increase in the rate. So it's nth order, so meaning this could be any integer, positive, negative, order if doubling the rate of concentration causes a 2 raised to n increase in the rate. That is based on this one. You see here the term double. So you have here a 2. If you change this to triple, this will be 3 raised to n. It's just it. Okay? So double, the base is 2, triple, the base is 3. So whatever is the degree of the increase in the concentration, that would be the same, that would be the base in here in which n is to be raised to. And that will be the amount of increase in the rate of your reaction. So take it from this particular pair here of information. Doubling makes it 2 raised to n. So you change the word double, that would also change the base in which n is being raised, in which you are raising to n. So note that the rate constant does not depend on the concentration. So this rate constant is your K, or we call it as the specific reaction rate constant. So the SRR in some old books, but they mean still K. So it's not dependent on concentration. Where is it dependent to? Your K. If order is could be, let's say, followed through, the order of the reaction could be taken from or followed through on the changes of the concentration. What about the reaction rate constant? Where is it dependent on? Okay, temperature. Thank you, Joshua. Very good. So temperature, your K is dependent on temperature. Your order is dependent on concentration, or is followed through changes in the concentration. So we move on. For first order reaction, I suggest, okay, somebody's writing temperature, correct, temperature also. Now, for first order reaction, you have in your kinetics then 2 formulas to use. Okay, it could either be based on concentrations. So I'd like to write in here. We can also write this as ln of Ca over Cao. Okay, equal to negative Kt. Now, when you, of course, use what you have learned in here in tackling problems in your licensure exam, of course, there's no need for you to plot. But just in case, if you'll be given concept type questions regarding the fit of your kinetic data, for it to be considered as first order, second order, and so on and so forth, then of course, there's a need for you to know this one. So for a first order reaction, the plot of the concentration of A at time t versus t is a straight line. Now, the slope of that line is the negative of the rate constant, and the intercept is the ln of the initial concentration. That's A sub O. Okay? Again, so the plot of ln of A versus t will have a slope of negative K and an intercept of ln of the initial concentration of A. If you're given a first order reaction, can you recall the other formula that was shared to you in kinetics then for first order? Let's see who can still remember. This is ln of Ca over Cao equal to negative Kt. What's another formula that we can use? You can write in the chat box. What's another formula that we can use? Here, we have 2. It depends on what the problem provides you. So let's say, for example, the problem did not give you changes in concentration, but it's stating that it's a first order reaction. It's giving you, let's say, conversion. What's the alternative formula that you can use? Or you can derive it in here from the one that is written. Okay, let's see. CA is equal to CaO1 minus XA. Very good. So if you change your CA to CaO1 minus XA, and you have CaO here, you cancel the CaO. So another formula to utilize is Ln of the quantity 1 minus XA equal to negative KT. That's for a first order reaction. Okay? So you can choose between these two formula to use depending on the information that is provided to you. Okay, that's it. So Joe Burns still remembers the other formula. Okay. Now, what about for second order reaction? Second order reaction, so it's like this. The second order reaction that is being referred to in here is this one. Okay, single species, because you could see in here that you only have A. So meaning the order of the reaction is just based on A. So if this is your second order reaction, the way this is written then, to help you recall, is like this. You have 1 over Ca minus 1 over CaO equal to Kp. Okay, this is your formula then for a second order reaction. Still, you can solve for whatever the problem requires if it's in terms of conversion. Just recall this very fundamental relationship between Ca and conversion. That is same, this is same is true, or the same is true with any species. This could be B, this could be C. Now, we change this to a different representation if we're talking already of the product. So this representation is for a reacting species. If let's say, for example, R is a product, the final concentration of R is CrO1 plus XR. So you don't subtract, but rather you add, because over time, you expect that the concentration of R, or the amount of R, will increase because it's the product. Okay? Remember these two, they are very fundamental in kinetics. Okay, now we proceed. So that's for a second order reaction, and it's stated here that if you're going to plot the reciprocal of the concentration of A versus time, you will have a straight line with slope equal to K and an intercept equal to 1 over the initial concentration. This is just like this is your Y, this is your MX plus B. So if you would be asked questions like this in reviewers, you will have questions like this. You will encounter questions like this in concept form. So this is how it's to be interpreted. So the equation or the formula taken from the evaluated differential equation was linearized. That way, you can come up with these relationships regarding the two data that you need to plot and the corresponding slope and intercept of this particular graph of the data. So we proceed in here. So that's for the second order reaction. The third order reaction was not written in here, class, but you can still have it derived on your own. You can derive it, or there's no need actually to derive, because I think there's a summary of formula already in Perry's handbook for that. If there's not, then just recall the fundamentals of how you derive the working equation for a particular reaction. So you just separate variables and have this, and have the left side and the right side of this equation integrated. That would be your formula to use if you're given a third order reaction. But it could be not like this if you have two species, like this, if you recall the cases that we have discussed in last semester, last year. It could even be like this. Right? So it's very important that when you have the rate here in terms of A, all your concentrations here will be in terms of A. So you need to express C sub B and C sub C in terms of C sub A. Going back again to that fundamental relationship I gave you, that CaO XA over A is equal to CBO XB over B, and so on and so forth. As long as you're able to convert the concentration of the other species that appear in your rate law to the form wherein it will be represented in the same manner as the unknown function in the derivative of your dE. So if your unknown function is C sub A, all of this should be in terms of C sub A. If the unknown function here is X sub A, all of this will be expressed in terms of X sub A. I know you know how to derive it. It will take some time, but it would be better as an exercise to know how you are to convert from one form into another. So I'm just writing it here that this is also fundamental, that that's equal to dxa dt. CAO dxa dt. Okay, negative dCA dt is CAO dxa dt. If you want to express concentration, or you want a different expression rather than concentration, let's say you want conversion because the problem gives you conversion. So this is the equivalent. Let's proceed. Now, what about half-life? This is a common question given in quiz bowls because it has already a ready-made formula. So the half-life, as early as your chemistry and your TE, is the time it will take for your reactant to be 50% of its original value or its initial concentration. Okay. Now, for a first order reaction class, this is the half-life. So I suggest you memorize it. Anyway, it's also, I think, in the handbook. This is already pre-derived from the first order rate law. Okay, we just assign Ca to be equal to 0.5 CaO, and we're able to get the half-life for a first order reaction. So it's dependent only on the rate constant. For a second order reaction, it's a different thing already because not only is it dependent on the rate constant K, it's also dependent on the initial concentration. Okay? So half-life for a second order reaction, half-life for a first order reaction. Now, what about the collision theory? This has something to do with the number of collisions, either similar species or not similar species collide with each other in relation to the rate of reaction. Now, since the rate law has no temperature term in it, the rate constant must depend on the temperature. So this was mentioned, this was already asked a while ago. So your K is dependent on temperature. So let's consider this first order reaction. So as temperature increases from 190 degrees Celsius to 250 degrees Celsius, the rate constant increases from 2.52 times 10 raised to negative 5. Not sure if you could see it, per second to 3.16 times 10 raised to negative 3 per second for this particular reaction. Now, what about the collision motor? So in order for molecules to react, they need to collide. Okay. The greater the number of collisions, the faster is the rate of the reaction. And the more molecules present, the greater the probability of collision because they're already crowded, and faster will be the rate. I'd like to go back to this one. Where do you apply this collision theory, by the way? In what particular system is this applicable to? The collision theory? Is it applicable to gaseous system, to liquid systems, to solid gas system? Particularly, the collision theory is applicable to what systems? What can you recall from your kinetics last year? The collision theory is applicable to, speaking of colliding, and speaking of more molecules present, the greater the probability of collision and faster the rate. gas system. Very good, Sarah and Earl. So collision theory is applicable for gaseous systems. Okay? Now, we proceed. Okay. According to Arrhenius, molecules must possess a minimum amount of energy to react. Okay, why? This is very elementary. Original bonds have to be broken. Bonds existing in your reacting species have to be broken. That way, new bonds can be formed. Without the breaking of the bonds, there won't be any new product that will be formed. Okay, so that's the very purpose why there is this minimum of amount of energy that is needed. That energy is the activation energy. Now, this activation energy appears in the rate constant, okay, according to Arrhenius, and it will be shared to you here on the next slide. So, Arrhenius theory gives you this formula for the rate constant and its relationship with the frequency factor. This is actually K sub O in our textbook, or the pre-exponential factor. And this is the activation energy, this is the absolute temperature, and this is the universal gas constant. That's your rate constant in relation to activation energy and temperature. So as we increase the temperature, of course, it's a given that your rate constant increases. Now, the fraction of molecules, on the other hand, F, with energy equal to or greater than the activation energy, if you would be asked what fraction of the molecules present in your system possesses this energy that is equal to or greater than the activation energy. That particular expression is actually just taken from this Arrhenius equation. This is the fraction of molecules in your system that possesses an energy equal to or greater than the activation energy. Okay, that was also covered in our class last year. Now, according to Arrhenius, we have this. And most of the time, class, this activation energy, if we're talking of SI set of units, as the unit kilojoule per mole. This is oftentimes big, or joule per mole. Okay? The R, in this case then, is suggested to be 8.314 joule per Kelvin per mole. Primarily because your activation energy is in terms of kilojoule per mole or joule per mole. So the R that you will be using is also having the same set of units. The T should be in Kelvin. Now, A is the frequency factor. I've mentioned it already. And A is the measure of the probability of a favorable collision. So not all collisions will result to a for your species to be reacted. So some are not proceeding as to the formation of the products, but those that produce the product or produces this particular favorable reaction that produces the product is measured in terms of this frequency factor, the probability of a favorable collision. Now, both this A, frequency factor, and your activation energy are specific to a given reaction. So, what we mean specific, it's only true for that particular system, for that particular reaction. We change the system, it follows that this also changes. The unit or the set of units of your K, the rate constant, and your frequency factor are the same. This exponential function here does not have any unit. It's dimensionless. So the unit of K, or rather I should say the units or the unit of A, your frequency factor is dependent on the K. Now, by the way, how do you determine correctly the set of units of the K? Given the order of the reaction, how do you write correctly the set of units for the K? Somebody suggest? It's very fundamental. So how do you determine the unit or the units of the K? The rate constant. Let's see. Dimensional analysis. There's a formula for it. What's the formula? In determining the set of units of the K, it's very fundamental. You should have the correct set of units for your K. How do you determine the set of units for your K? Let's say we're talking of a rate constant wherein your rate law is for a homogeneous liquid system. So what is the unit of the K? Because when you speak of gas, our rate law can also be expressed in terms of partial pressures, right? So the unit of the K will be different if it's partial pressures. Let's say we talk about the common way of expressing the K. What's the set of units? The time raised to -1 and concentration raised to -1 minus n. Very good, Socrates. So your K is time raised to -1 times concentration unit raised to 1 minus n. Although dimensional analysis will help you, but it's really very important that you know this so that you need not do dimensional analysis. Right away, you know what would be the corresponding unit or units for your rate constant. Okay, so take note of that. That's very simple and it's very fundamental also. Now we move on. How do we determine the activation energy? So if we have a lot of data, we can determine the activation energy and the frequency factor graphically. But you won't do that, of course. But you have this equation from Arrhenius that will lead you to the amount of the activation energy and the frequency factor. From this above equation, if you plot the ln of K versus the reciprocal of the absolute temperature, it will give you the slope of the line. So this is also very important. I have read it several times already in the viewers. It will give you a slope for that line equal to negative of the activation energy divided by the universal gas constant and an intercept equal to the ln of A. And from here, you have the relationships in, I'm not sure if I have written it here, so it's there already. It's here. So, okay, we will have it extended. So this is it. It's very important. You plot the ln of K, plot the ln of K versus 1 over T. The slope of that would be this activation energy divided by the universal constant, and this will be the intercept of that line. Okay? Linearizing Arrhenius equation. So that's the way you do it. Now, we have these formulas. If you're given a set of data or a pair of data for K and temperature, sorry class, I got disconnected. Okay, I will share again my screen. So as I was saying, the ln of K sub 1 over K sub 2 is equal to the activation energy divided by the universal gas constant multiplied to the difference of the two reciprocals in temperature. If you have K1 here, you have here T sub 2. But if you intend to have T sub 1 here and T sub 2 just like in